So, right, so I'm continuing the discussion of, which is addressing the following question: what do laminations and foliations tell us about the topology of 3 manifolds? So again, we have something in the 3 manifold, and we want to be able to derive some type of topological data, information. So today I want to talk about essential laminations. So what is a lamination? A lamination is just a foliation of a closed subset. So more specifically, if we're looking at a codimension 1 lamination of a 3 manifold, that means that you have this 3 manifold, and just like you have foliation charts, you have lamination charts. So a little lamination chart is a little R2 cross R, and the lamination is supported not on the whole R2 cross R like a foliation, but rather it's supported on a R2 cross some closed set, and that is the laminated structure is just the product structure. So you have these various leaves that are passing through in this closed set. So that's what a lamination is. Now, there's certain there's one important thing to note, is that, of course, unlike a foliation, a foliation fills up the whole manifold, but a lamination doesn't. So in particular, has these complementary regions. So it's important to understand really not so much the complementary region, but the complementary region together with the leaves that lie on the boundary. So here's a complementary region, and V, and you can see there's 3 boundary leaves. So if you take V plus its boundary leaves, that's taking the completion with respect to V as a subset of the manifold has its induced path metric. So its closure with respect to the path metric is just adding one of these boundary leaves. And so you should think of, when you think of a closed complementary region as this thing, somehow you could think of it out by itself. So, right. So, right, so now we're ready to define what essential lamination is. So an essential lamination is a codimension 1 lamination which has some nice properties. So what's an essential lamination? It's a lamination which has no 2-sphere leaves. Every torus bounds a solid torus. And if you have a closed complementary region, then the boundary leaves are pi1 injective in the complementary region. And you have this extra condition called end incompressibility. So let's not worry about end incompressibility for the moment. I mean, so this looks like a lot of words, but it's actually a really simple idea. So there's no S2 leaves, okay? I mean, what does it say, for example, if the lamination's a foliation? Well, condition 2 is vacuous since there's no complementary regions. So in condition 1 says no torus leaf bounds a solid torus. So for foliations, something is essential if it has no Rave components. This is a verbose way of saying no Rave components, but we have to have a condition on complementary regions. And the condition is that the boundary leaves actually pi1 inject into not the whole manifold, but just if you look at the complementary region by itself, that thing, the boundary of that V is pi1 injective. And then there's this end compression condition, which, well, basically rules out things like this, which is somehow you have this monogon, which is sort of this, which is properly embedded in this complementary region, and somehow it can't be deformed into the boundary. So a manifold that has an essential lamination we'll call laminar. So actually these two good words, end incompressible and laminar, I mean, we thank, Alan Hatcher, gave us these words. So you can see that essential lamination is, so a taut foliation, or Raveless foliation, is an essential lamination. And so, and also if you just have say a 3-manifold which is irreducible, and then you have a pi1 injective surface in that 3-manifold. Well, so those 3-manifolds called Hacken manifolds. So a pi1 injective embedded surface is also an example of an essential lamination. I mean, in that case, you just have this nice compact surface, and it's pi1 injective, so it's easy to check those conditions. So the point is that Ulrich, Ortel, and I sort of introduced this idea of essential lamination to simultaneously generalize the notions of incompressible surface and Raveless foliation. So it turns out there's a whole lot of essential laminations. So here's one example. So suppose you take a knot in S3, and suppose the complement of that knot fibers over the circle with pseudo-knots of monogermy. So that means that topologically, the knot complement is obtained by just taking a surface cross I and gluing, surface cross 0 to surface cross 1 by some homeomorphism. Now let's assume that homeomorphism is pseudo-Nassau. So as Sergio reminded us yesterday, that means by Thurston so we have a homeomorphism of the surface to itself. And by Thurston, there's a one-dimensional lamination in that surface, which is taken to itself under the homeomorphism. So since that one-dimensional foliation is invariant under a homeomorphism, you could construct a two-dimensional foliation by suspending that lamination. So in particular, so what that means is you have a one-dimensional foliation on surface. When you multiply times I, you get a two-dimensional foliation in surface cross I. And the fact that this one-dimensional foliation is invariant under monogermy is that when you glue the top to the bottom, these foliations match up. So now you can just check that these foliations are essential. These laminations are essential, right? Because, well, there's no torus or two-sphere leaves, by construction. So you need to just check the complementary regions to see if they're okay. And a typical complementary region, well, in the surface is just some trigon or fourgon or bigon or something, some n-gon where n is bigger than 1. So in the suspended thing, the complementary regions go like some n-gon cross I with some gluing, maybe with some rotation. So that's what a complementary region looks like in here. And look, so this complementary region is a solid torus, and a boundary leaf is just an annulus that's going going in a pi1 injective way around the boundary. So it's, I mean, it's it's easy to check that this complementary region is, I mean, it has incompressible boundary and it has no end compressions. And then there's another type of complementary region corresponding to the boundary. So in this, so there's, well, so here the complementary region's like an annulus cross S1, and it's completed by filling in the boundary of the knot here, and then there's the leaf over there. I mean, in this case I drew it like there's one cusp, but there could be 2 or 3 or some finite number, well, bounded by the genus S. So this is an example of a central lamination in a knot complement. Now, but this essential lamination is disjoint from the knot. So there's a temptation to take that. So we've drilled out the neighborhood of the knot, and so now, since there's no lamination there, we just might as well just fill it back in by maybe a different surgery. So there's this, in manifold theory, this idea of just drilling out things and filling them in. So this idea of Dane surgery, we just drill out a solid torus and put it back in a different manner, and we get a new manifold, maybe a homology sphere, something. So in this new manifold, we have this old lamination viewed in the new manifold, and you ask, well, is that lamination essential? Well, the answer is maybe yes, maybe no. But you have to check that there's no torus or sphere, so you just have to check the complementary regions. And all the complementary regions are the same, at least the ones that are disjoint from the knot. Their topology doesn't change. There's only one complementary region that might be interesting, and that's the one that contains the knot. Well, it turns out that, well, there's one bad surgery, basically the surgery where you sort of do attach the boundary of the meridional disc of the surgery torus sort of is parallel to these cusps. Well, okay, that's bad. So there's one bad surgery, but besides that, notice that the complementary region is now going to have some number of cusps, and this number is exactly going to be the number of times the meridian disc of the surgery, the filling torus, crosses the cusp locus. So here, so when we fill in this thing, we're attaching a meridian, like a D2 cross S1 in here. So the boundary of a D2 cross point is an essential curve on this boundary torus. So you could just kind of push that boundary curve out, or maybe better, push this cusp locus into the boundary and count the number of intersections. And so that number is this. And as long as this number is bigger than or equal to 2, again, you get an essential lamination. So the Dane surgery space, is parameterized by the relatively prime integers in z plus z. And there's only basically one line of slopes that are going to give you sort of one cusp here, which is bad. But all the other lines, since most of the surgeries are going to give you central lamination. And then later, Lee Mosher and I found foliations, laminations transverse or almost transverse to finite depth foliations. And they have the same property. So it's a theorem that if you have any knot in S3, then off of a line in Dane surgery space, there's going to be an essential lamination in the surgered manifold. So there's lots of examples of essential laminations, and we'll see more real soon. So here's a theorem, which is the essential laminations version of Novokov's theorem. So if we have an essential lamination in the 3-manifold, the conclusion is that if you have a leaf, leaves inject leaves are pi1 injective in the 3-manifold. And if you have a curve which is transverse to the lamination, and it's efficient, whatever that means it represents an infinite element of fundamental group. And also the universal cover is R3. In particular, the manifold's irreducible. So this is 1 and 2 are exactly the corresponding ideas, results from Novokov's theorem, and 3 is, of course, Palmeira's improvement to Novokov's condition of pi 2 of m is trivial. So, right, maybe I should say what efficient means. You see, if you have a foliation, if you have a curve transverse to the leaves of a foliation, then, well, that's a transverse curve. But if you have a lamination, that curve is going to pop out, is go into the complementary regions in big sets. I mean, it's going to intersect the lamination only in a closed set. So there's going to be spots where here's the lamination, and here's this curve which is going to sort of pop out. I mean, so here's the curve going through here, and it's going through the lamination. So there's a silly thing that could happen is, of course, I mean, if you look at this picture a little bit larger, it could be that maybe these leaves are just coming back, that there's this curve is just intersecting sort of in a silly way. Well, in other words, you can see here's a little interval where it's going across a closed complementary region, and that curve could be homotoped into a leaf. So this is bad. This is not efficient. So basically, efficient is just it's the reasonable condition that there's no silly things going on in that curve while it's outside the lamination. Well, actually, like a curve going probably around here is going to be efficient. I mean, it doesn't look very efficient, but or maybe that curve itself isn't very. Anyway, there's a curve, for example, that cuts across like this. I mean, it's cutting across in an essential way in the complementary region. That's efficient. If it goes there and sort of circles back, comes back, it's not efficient. So, right. So what I want to tell you now is the sort of Laminations versions of Foliations theorems that we've been talking about. So here's the Laminations version of the Novokov theorem, and here's the Laminations version of the Hepligger, Rave, and sort of part of the Palmeira theorem. So if you have a foliation, when you pass the universal cover, you have this foliation of R3 by planes, and then you can sort of contract leaves to points, and you get the space of leaves of the universal cover. So, and for foliations, that was a one-dimensional manifold which was simply connected but not necessarily Hausdorff. So what's the analog for laminations? Well, for technical reasons, just make a slightly simpler case. You have a central lamination, and assume there's no isolated leaves. So now you lift the lamination up to the universal cover, and then to get this sort of the analog of the space of leaves, what you do is you take the universal cover and you mine out by equivalence relation, where you maybe take a closed so you contract two types of things to points. closed complementary region, you just contract that to a point, or leaves which aren't boundary leaves of closed complementary regions, you contract them to point. So if you could think of a closed complementary region as maybe a three-dimensional, it's like a leaf that's maybe three-dimensional instead of a typical leaf which is two-dimensional. So if you think of it that way, then just contracting out is just like by contracting out these things, you get the analog of the space of leaves. But you don't necessarily get a one manifold. You get something which is more tree-like, sort of reflecting the tree-like behavior of the lamination. And so we get something called an order tree. It's kind of like an R tree without the metric, and it's often non-Hausdorff. But nevertheless, we still have the analogy of Rave's theorem, the Rave-Hepligger theorem, which is that order trees, there's a one-to-one correspondence between order trees and laminations of R2, well, which are, well, sorry, which has order trees. So that includes simply connected, why did I do this? So order trees, so there's a one-to-one correspondence between order trees and laminations of R2 with no isolated leaves, at least the way I defined it here. So well, modulo an equivalence relation, which is just like we need an equivalence relation in the Rave-Hepligger thing to worry about maybe Rave components that are pointing this way or that way and some other ordering condition. What? Well, order tree is sort of the generalization of simply connected one manifold. So I mean, locally, an order tree has all these various embedded intervals in there. I mean, subintervals, subspaces that are homeomorphic to the closed interval, and it's sort of a cannibal union of such things. But when you add more and more of them, there's a branching, and they might branch in a non-Hausdorff manner. But sort of their geometric realization is order trees are just like laminations of R2 without isolated leaves. And we also have this sort of, well, laminations version of Palmeiras' theorem that if you have an essential lamination, then its lift to the universal cover is like a lamination in R2 multiplied by R. Actually, there's one thing really neat here, which is that a little addendum to this Palmeira-like theorem, which is that suppose you have a simple closed curve on a leaf. Then what does that simple closed curve look like in universal cover? Well, it turns out that you can identify the universal cover with lamination R2 cross R in such a way that the preimage of that leaf looks like just a discrete set of points on R2 multiplied by R. So not only can you topologically conjugate the lamination in the universal cover so all the leaves just look vertical, but you could actually do it so that the preimage of this circle on a leaf, assuming the circle is homotopically non-trivial, so that circle actually looks just totally vertical, just a bunch of vertical arcs in R3. So this is really kind of neat because it says that simple closed essential curves and leaves are sort of lift to unknotted, an unlinked link, the unlink on an infinite number of components in R3. It's just like the preimage of a geodesic in a hyperbolic 3-manifold, a simple closed geodesic, lifts to just an unlink in hyperbolic space, an unlink of arcs. So anyway, I should say there's a whole lot of, well, this is just what I've just told you is maybe the analogs of theorems that were established for foliations, that I discussed for foliations. But, but there's still, the essential laminations have been around for maybe 12 years now, but there's really not as much known as we'd like about essential laminations. And so while I'm discussing them and what we know about them, I think it would be useful to just mention a lot of things that aren't known. So in particular, you have this order tree, whatever it is, and maybe here's the problem. Develop a theory of fundamental group of so you develop a theory of group actions on order trees, particular group actions coming from fundamental groups of 3 manifolds. So there's 2 sub-questions, which are, so which 3 manifold groups act on these order trees, and if you have a group acting on an order tree, is that equivalent to saying that the manifold's laminar? Or a related question is, well, is there anything else you can say about the manifold? So for example, if we're not talking about order trees, but we're talking about, say, simplicial trees and 3 manifold groups acting on simplicial trees, well, Stolling thought about that a long time ago, and that's like simplicial trees are dual to preimages of embedded surfaces. And so if you have a group action on a simplicial tree, Stollings would say, well, there's an embedded surface. Or if you have a group action on an R tree, which acts isometrically, then Morgan and Shalin would say, well, there's a essential measured lamination. So maybe one of the fundamental theorems in this, one of the basic questions in the subject is to develop maybe some theorem like that for laminations, order trees, and also maybe order trees are just of interest in themselves, so understand what groups act in them. So that's an important question. So here's another question, which has been bothering me recently. Which is, when I'm thinking about the definition of essential lamination, we have this condition on end compressibility. So what if you just remove this condition on end compressibility and you retain basically all the other conditions on essential lamination? So well, this was about 7 hours ago, but I came up with this word, loosesse or something, loosesse. So that's like a loose essential lamination. I don't want to say loose essential, because that means that loose is modifying essential, but essential means essential, and essential laminations aren't loose. So a loosesse means loose essential lamination. So here's the definition. It's just like an essential lamination. So there's no S2 leaves. The leaves pi1 inject. Well, we need this extra condition, the complementary regions, which this other condition is automatic for essential laminations. Pi1 complementary regions, pi1 inject. Complementary regions are irreducible. But we have this extra condition that some closed complementary region has an end compression. So here's a question. Are these things at all interesting? For example, I'm pretty sure the universal covers R3, but I put a little question mark because I thought about that 7 hours ago, but maybe these things actually come up in life because, for example, if you take these examples I mentioned before, say bundles, if you take one of these surgery on Dane filling on a knot complement that fibers over the circle. Well, there's this infinite number of surgeries, this line in Dane surgery space, which gives laminations which fail to be essential because of this, because there's a complementary region which is a monogon cross S1. So there's so it has this end compression. But it seems to me perhaps not impossible. Maybe it is, but it seems to me not impossible that maybe all but finitely many of those are these Lucas laminations. So anyway, that's another thing to think about. So, whoops. Right. So now here's another question, one of the most fundamental in the subject, which is, what manifolds are laminar? Now, there's just a tremendous number. Well, there's a lot of examples that are just, if you look at any one of them, they're just really beautiful, and they're just, you know, there's this whole list of people, but each one of these constructions is you know, is really something else. And so, for example, Fried and Giss and Thurston, I mean, they knew, for example, that if you have the suspension construction, which I mentioned before, is just actually a variation of something they know, which, namely, that if you take a fibered knot and you look at the monogery and suspend it, and if the complementary regions are of a certain type, maybe there's even number of prongs and there's an even number of rotation, then you could actually fill in the complementary regions with saddles and get Rave-less foliations. And Thurston's construction in his Norman Topology of 3-Manifolds is really great constructions of taut foliations in there. I mean, Hatcher had a lot of foliations, laminations on surgeries on two-bridge knots, and Ortel found a lot of some examples of projective laminations, and Naimi and Delman and Roberts sort of generalized some of Hatcher's work. In particular, Naimi and Delman found that if you have a two-bridge knot, all the non-trivial surgeries have essential laminations. I mean, I'm ignoring the torus two-bridge knots. And in fact, by Delman and Roberts, that all non-trivial surgeries on all alternating knots have essential laminations. And then if you put all these various constructions together and some other constructions of theirs, you get that all knots of less than or equal to 9 crossings, which are not torus knots, have essential laminations in all the surgeries. So when you open up the knot tables, you're talking about most of the manifolds you get have these essential laminations. And Joe Christie has a way of deforming standard spines to construct essential laminations. So that's the good news, of course. But there's really huge, you know, there's just a completely open question. I mean, it's just a lot of, it's not really known, really, the extent of how many essential laminations there are. So, for example, if the -237 pretzel, if you do 35 half surgery, it's not known whether that has essential lamination.
Is the 9 over there sharp?
Well, I guess if you're actually going through the knot tables, 10-139 is the first one that you'll run into that has the property that it's not a torus knot. It's not known that all the surgeries have essential laminations. I'm sure by these guys, at least half of them do, in some sense. Now, here's another constraint on the essential laminations. There's a theorem of Klaus and Britton, Hamm, 1990, which says that if you have an essential lamination in a ciphered fibered space, remember, a ciphered fibered space is a manifold foliated by circles, then it has a sublamination which is either horizontal or vertical. So in other words, if you have essential lamination, then after an isotopy, you could find a sublamination where it's just a union of fibers. Those are the vertical ones. Or sublaminations transverse to the fibration. Then those are the horizontal ones. And in particular, if the manifold to start with was non-Haken, had no Pi1 injective surfaces, then actually you can isotope the lamination to be horizontal, transverse to the ciphered fibers. And that's really cool because such laminations, I mean, the fact that they're transverse to the ciphered fibers means that basically the gaps in the complementary regions are all eye bundles. In fact, so that means you can fill it in to a foliation. So, and there's this long history here of foliations on ciphered fiber spaces that are transverse to the fibers. There's a classical Milner-Wood inequality which solves the problem of which circle bundles have foliations transverse to the fibers. And Hirsch, Newman, and Eisenbud generalized that to certain ciphered fibered spaces, and Jenkins and Neumann generalized it to other ciphered fibered spaces, and made a conjecture as to exactly which ones of them had foliations transverse to the fibers. And actually Naimi verified the Jenkins-Neumann conjecture. So we know exactly, so for the ciphered fibered spaces, we know exactly which ones have essential laminations. So that's really a long story which was done. So right, so here's, well, let me just, more questions than theorems in this talk, but, so here's another question. Well, so in particular, we know about ciphered fibered spaces. What about hyperbolic 3-manifolds? Are they laminar? Are they virtually laminar? That is, there is some finite cover which is laminar? Or here's another question. Can you find an algorithm to decide if a 3-manifold has an essential lamination? And sort of related to that is a question of, well, suppose you have a branch surface, something like this, just some 2 complex that lives in the 3-manifold, which has sort of this local structure, one of these local structures. These planes are sort of coming in tangentially. They're like train tracks. So here's a question. Do these things, if you're given one of these things in a 3-manifold, does that carry a lamination? That is there a lamination that lies nearby to this thing, which is somehow a little neighborhood of this thing captures the whole lamination? Now, that's an extremely subtle question, I think, because I know that some people have worked real hard on it, and it's really tricky. And it's so subtle that there's this theorem of Mosher, which I'm not going to call a theorem, I'm going to call a warning. And it says that if you leave the realm of branch surfaces in 3-manifolds and of embeddedly carrying laminations, and you go to the realm of sort of abstract branch surfaces that are sort of 2 complexes that live sort of in its own setting, which have this local structure, and instead of and you talk about laminations on such things, which you should maybe think of as immersed, as complete immersed surfaces that live on this 2 complex, which respect the branching, then Lee Mosher showed this problem of this is there's branch surfaces that have that's undecidable whether that branch surface carries a lamination, because he reduces this problem to a problem about tilings, which is known to be undecidable. So, but let me mention another theorem of Britton, Hamm, which is the reason why this question of do branch surfaces carry laminations is interesting because one reason is because of this theorem of Britton, Hamm, which is that if you have an essential lamination, then if you have a laminar manifold, this manifold has a essential lamination carried by one of some actually relatively small number of branch surfaces, 3 to the t, where t is some number of tetrahedra in a triangulation. So if you have a 3-manifold which has a triangulation. Actually, the triangulation, I mean, you don't need actually to be classical triangulation. It just needs to be some type of cell complex where the cells are tetrahedral. Then he comes up with like 3T branch surfaces, and so you could take one of these manifolds, which are maybe candidates not to have essential laminations, and he'll provide you the branch surfaces, and if you could just check whether they carry laminations and check whether those laminations are essential, well then you've done something. So anyway, here's another question while I'm talking about branch surfaces. So right. So I said that essential laminations were sort of introduced to simultaneously generalize the notions of piling injective, or essential laminations were introduced to simultaneously generalize the ideas of Raveless foliation and pi1 injective surface in a Hawken manifold, in a closed-oriented manifold. So I just wanted to remind you of some classical theorems about Hawken manifolds. And there's the remarkable work of Waldhausen in 1968, and he showed that just for simplicity, I'm assuming everything's atoroidal. So he showed that the universal cover of Hawken manifolds are R3, homotopic. If you have a manifold homotopy equivalent to a Hawken manifold, and this manifold, so you have a Hawken manifold homotopy equivalent to a closed irreducible 3 manifold, then they're actually homeomorphic. And in fact, so he also showed that 2 homeomorphisms that are homotopic are actually isotopic. So another way of saying 2 is, I mean, 3 manifolds, Hawken 3 manifolds are k pi 1s. So if the classic algebraic topology, the homotopy groups, if a Hawken manifold, another manifold has the same homotopy groups, then are they the same manifold up to homeomorphism? And that's a reinterpretation of 2. And there's a homotopy theoretic interpretation of an algebraic topological interpretation of 3 too, also. And then there's Johansson's theorem that the diffeomorphism group is finite up to isotopy. Of course, there's Thurston's fantastic theorem that Hawken manifolds, which are atoroidal, have hyperbolic structure. So knowing all these theorems about Hawken manifolds and manifolds with essential laminations are supposed to be generalization of such. I mean, how well have we done about proving such theorems about essential laminations? Well, I'm afraid to admit, well, it's just a fact. As far as I know, maybe someone else can tell me otherwise, that when it comes to taut foliations, essentially nothing is known about these theorems. I mean, there's some technical results that may or may not prove useful, but it's really hard for me to say that there's a single result in the subject for taut foliations on this line. Of course, there's Palmeira's theorem that universal cover of manifold taut foliation is R3, but so it looks like we've made no progress along this line. But again, there's I mean, if every lamination was either taut foliation or raveless foliation or high injective surface, I mean, what's the point of defining essential lamination? So there's a genuine essential lamination. So a genuine essential lamination is a lamination that's genuinely not a foliation. So what does that mean? I mean, you can imagine taking a foliation and, I mean, there's these leaves are going all through the manifold, and there's this operation of splitting open leaves. You can imagine someone just taking a little bit of leaf and kind of creating a little pocket and just blasting it open. So there's this way of turning foliations into sort of nowhere dense laminations. But that's not really a genuine operation. So I guess Wilkes and I had this definition, and so genuine lamination means it's really not a foliation. It means, so there's some complementary region which is not an eye bundle. If the complementary region is an eye bundle, you can just fill it in, just like that, and get a foliation, get a raveless foliation. And let me just say that the construction that I mentioned of surgering bundles, or the more general theorem of motion, says that most manifolds obtained by surgery on a knot actually has a genuine lamination. Now, when we talk about genuine laminations, we actually do have some little bit of progress towards these questions. So here's the theorems that Will and I have, which is that if you have a genuine lamination, then the fundamental group of the 3-manifold is negatively curved in the sense of Gromov. And second is that, well, there's a finite number of diffeomorphisms up to isotopy. And the third theorem is that homotopic homeomorphisms are isotopic. Well, actually, we don't know that in full generality, but we know that that's true of some complementary region is a solid torus, which is not an eye bundle. So, for example, all these laminations that come from, with Mosher, those all are of this type. So
you're assuming atoroidal?
Yeah, I'm assuming atoroidal here. That's right. Right, atoroidal. Yeah, thanks. So questions, what is it about genuine laminations that you can actually prove something while with foliations we have trouble, we don't have, it's difficult. Well, the point is that that essential lamination has non-trivial gut. That is, a genuine lamination has this eye bundle, has a complementary region which is not an eye bundle. And actually, if you analyze this complementary region, you can actually break it up into sort of non-compact eye bundles together with a compact thing. And this compact thing is the gut. So this decomposition is just a baby form of the Jacob, Scheel, and Johansen sort of characteristic manifold splitting. It's a really easy form of that. And so there's this core of the manifold, this gut, which you can actually grasp in your hands. Well, with a taut foliation, there's all these leaves there, but they're kind of slippery, well, I don't know how to really get a hold of them. So let me give you a really vague idea of why, if you have an essential lamination, or a genuine lamination has group negative curvature. Well, let's look at a special case. So let's look at, say, laminations coming by surgering the bundles. So in that case, the complementary regions are all these tori. So essentially, you could just collapse out the complementary regions and get a singular foliation. So Gromov showed that a manifold has word hyperbolic fundamental group if and only if it satisfies a linear isoperimetric inequality. So what that means is that if you just take any curve, then that curve bounds a disk where the area of the disk is not huge relative to the length of the curve. So you can't find a sequence of curves where the ratio of the area of the disk of a disk it bounds, of a sort of least area disk it bounds, and the length of the curve gets bigger and bigger. So the area of the disk is up to multiplicative constant is approximately the length of the curve, bounded by the length of the curve. So the vague idea is that here you just look at this curve, which is, say, transverse to the, well, take random curve and homotopically trivial curve in the manifold, span it by a disk, look at the intersection of the disk with the lamination. Well, it turns out that you can show that either the area of the disk is pretty much the area of the lamination, the area of the disk is pretty much the length of the boundary curve, or you can show that the area of the disk is just the intersection number with these sort of singular points. But every time you have an intersection with a singular point, by the Poincare-Hopf index formula, you get a tangency at the boundary. And, well, of course, tangencies at boundary could have been really close to each other, but actually, by some general nonsense, you could assume that this discussion is only about curves where there's definite distance between any two tangencies. So in summary, that if you have a curve, you bound it by disk hits the lamination. So the area of the disk is approximately the intersection number, which is approximately the number of tangencies, and the number of tangencies is approximately the length, because there's definite separation between tangencies. So anyway, that's a 2-minute, just a hint to give you maybe what to look for in this proof of this theorem. Okay. Okay, well, there it is. So, right, so I guess I'm running out of time here, but I wanted to give you a quick idea of Britton-Hamm's theorem. I guess I mentioned 2 theorems of his. One was that you could, if you have a lamination in a ciphered fibered space, you could make it either horizontal or vertical up to passing sublamination. Or there's this bounded number of branch surfaces that carry some lamination if the manifold's laminar. But I've run out of time. But let me at least mention sort of one sort of neat thing here, which looks like lamination's different from sort of compact surfaces. I mean, for example, here's this Rave lamination on this triangulated annulus. And if this lamination was compact, then sort of with a finite number of finite isotopy, you could just make it intersect sort of in a nice way, in an efficient way, the one skeleton. I mean, here this guy's kind of inefficient. It's non-normal. So the temptation is to make it normal by just doing an isotopy, and so you do an isotopy, fix him up, but when you do that, now you have another arc that's bad, and then you fix him up, there's another arc that's bad, and you fix him up, there's another arc that's bad, and when in this case you've done it 4 times, you get back to the same lamination. So it looks like a sort of a hopeless procedure. But Britton-Hamm has this sort of principle, this way of taking laminations and trying to put them in sort of a normal form with respect to a 2 complex by sort of doing this type of operation in an infinitely fast manner. And somehow these theorems that I mentioned, are done by sort of using this idea. So, actually, maybe I just should add a few words here. Okay. So let me just. So anyway, one thing I've looked at is I've tried to understand what he does, and I mean somehow what you have is this lamination, and you're trying to put it in some standard position with respect to this 2 complex. So you kind of do a little so it's kind of a mess at one spot, and you kind of do a little isotopy and you fix it up, and then there's another cell, you fix it up here, another cell, fix it up there. But every time you fix it up, you make a mess someplace else. And so you fix it up here, you make a mess there. So now you can cycle through all the cells and you come back to the first cell and it looks like a complete mess. So now you've kind of fixed it up there again, and so you just repeatedly, just infinitely many times, just go through all the cells and you fix it up over and over again, and somehow you just take a limit, and somehow you lose consciousness for a moment, and then you wake up and suddenly you have this lamination which is essential, well maybe after some modification, and it has the properties that you're looking for. So actually I've made the effort to try to stay conscious, and so this last moments before this lamination gets transformed into this new one. So the point is he starts with one lamination, comes out with a new one. So I've tried to understand that operation sort of without losing consciousness. And so anyway, let me just tell you a couple theorems. Well, so here's this theorem 2, which is that if you just fix a manifold, then there's a finite number of branch surfaces that carry any nowhere dense lamination. So in a sense, this says that there's these branch surfaces. These are nice compact objects, and there's a finite number of them. So therefore, well, of course there could be infinitely many different laminations, but up to there's really only finitely. They're pretty close, in a finite way. So in particular, if you have a taut foliation, in particular, there's a triangulation with the property that if you given any taut foliation, that you could make the triangulation look standard with respect to that foliation. That means that if you look at any tetrahedron of that triangle, any tetrahedron of that triangulation, then you could find a foliations chart where that tetrahedron looks perfectly straight. Nice linear tetrahedron. I mean, up to change of coordinates locally, it looks just totally linear. So this says, so the theorem, say for taut foliations, is that there's some triangulation, so that given any taut foliation, it can be made to look standard with respect to that triangulation. So in particular, we get this. So here's a corollary. Which is that there's a finite number of taut foliations which have the following property: that if you're given any other taut foliation, then up to isotopy, that taut foliation can be isotoped so that the plane fields of that taut foliation are maybe epsilon close to the plane fields of the other taut foliation. So in a sense, of course, a given manifold can have infinitely many different taut foliations, but this theorem says that if you say two taut foliations are the same, if up to isotopy, you just homotop the plane fields by some I mean, by some epsilon amount, isotop at epsilon amount, and go from one to the other, then there's only finitely many. So I call such things coarsely isotopic. So with a little corollary, I mean, there's this Kronheimer-Rovka theorem which says that there's only finitely many homotopy classes of plane fields of taut foliations. And I suspect this idea of coarse isotopy is a much finer separation of foliations than homotopy. But nevertheless, there's still only finitely many. So okay, so that's all I have to say.
What are the measures that Kronheimer and Barak?
Well, I mean, they use the Cyber-Witten's theorem. They use some of Yasha's theory and Thurston, and so it's really, you know, it's high-powered stuff. But for me, just get in there and just, you know, move the leaves around and just keep your eyes open, and, you know.
So let me ask you another question. This is pre-frequency. Is it a server or?
Well, this is it's being written down. It's up to version 0.52. So it's.
Are you saying you have your own proof of this growth?
Well,
That's the point of your exposition.
Yes, sir.
Another proof of this corollary in the epsilon isotopic form.
That's right. That's right.
Yes. Well, since it's the end of the series, so I see, I mean, you get close to the structure theorem for the set of dispositions. What we say is finite.
Okay.
So you have any more structure in the type?
Well, I don't know. I mean, I think that's a good question, and I think, you know, I tried to express in this third talk that there's, I think, far more interesting questions that need to be sorted out than we have answers to. Well, thanks for listening.